Hello everybody, welcome to my presentation. It is my honor to be presenting in University Scholar Conference Engineering and Innovation USA 2021. Today I am presenting on design, fabrication and performance analysis of Pico-Francis turbine with experimental and computational methods. I am Prabin Dhakal and I have completed my BE studies in mechanical engineering from Kathmandu University. I am currently working as the Vice President of Nepalese Space Research Association. These are the outlines of my presentation. The estimated power potential in Nepal is about 83,000 MW, and the total economically feasible hydropower potential is about 42,000 MW. Despite this enormous opportunity, Nepal has not been able to harness even 2% of the total power potential. One of the main possible reasons for this might be due to the technical and financial limitations. Among the harnessed power, majority of the plants in Nepal are run-of-river type hydropower projects, and Francis turbine is one of the most widely used turbine types in Nepal. Many rural communities of Nepal are still deprived of electricity, where Pico-Hydro with fabricated Francis turbines could be the solution. Pico-Hydro covers hydropower under 5 kW. Pico-Hydro equipment is small, compact and can be installed at a small capital investment. Turbine Testing Lab is an institution established with the motive to address technical and social aspects of hydropower development and turbine-related issues. Kathmandu University and Turbine Testing Lab, in collaboration with many universities and industries, have supported and worked on several research projects to develop and improve the design of hydropower turbines. Further, Kathmandu University has also focused on hydropower development with introduction of hydropower subdivision under the Department of Mechanical Engineering in undergraduate studies. Several extraordinary milestones have been achieved in the research and development of hydropower in Nepal. The design and study of hydropower development project in undergraduate level seems the next logical step. The research focused in Pico-Hydro could provide electricity in rural communities of Nepal, while the research could help produce skilled and experienced human resources. The research discusses the design and fabrication process of 2 kW Pico-Francis turbine components along with its experimental and numerical analysis. Before getting into design parameters, first of all let me explain briefly about the Francis turbines. Francis turbines are a type of reaction turbines. These are the most widely used hydro turbines in the world with 60% global capacity. They operate within the speed range of 0.2 to 1.5. They can be divided into high head, medium head and low head Francis turbines, obviously according to their operating head. Now, this picture shows the Francis turbine used for this research. The turbine runner was provided by Turbine Testing Lab, which was fabricated through casting process in 2013. The design parameters for this runner are shown in this table. These design parameters are used to design and fabricate the components of Pico turbine such as spiral casing, vane and draft tube. The study was part of second and third year academic project. So to avoid any complications, guide vaneless turbine was designed and the length of the vane was increased to compensate the lack of guide vane. I'll be very brief in design methods due to time limitation. First of all, height of the guide vane, inlet velocity and length of the guide vane is calculated. Also the optimum inlet angle of the runner is determined. Then the length of the vane is determined. Then the length of the guide vane and length of the vane is added to obtain the total length of each vane. The vanes are kept such as to match the inlet angle of the runner. Then the discharge and diameter of each section of this spiral casing is determined. Finally, the inlet pressure is determined to calculate the length of the draft tube and diameter of the draft tube. The design parameter is provided in great detail in the submitted paper for the conference. After the design, the structural domain of each of these components is created and assembled in student version of SolidWorks 2016. Then latency software is used to create surface development for the cutting area of each of these sections of spiral casing and the draft tube. This figure shows the sample of the surface development created for this section of the spiral casing. As mentioned earlier, the runner of the turbine was casted and provided by the Turbine Testing Lab for this project. So first of all, combined stevens are fabricated and then well machined and welded in between two rings to create the steering as shown in this figure. For spiral casing, first of all, metal sheet is cut using the outlines of the surface development. Then the cut surface are rolled using the cold rolling process to create each of these sections of the spiral casing, and then each sections are welded together to create the whole spiral casing. Now, draft tube is also fabricated with the same process of cutting the metal sheet using surface development, cold rolling, and then welding to get the fabricated draft tube as shown in this figure. The remaining parts such as flanges are fabricated from machining. Now finally the assembly of the turbine components is done, and this figure shows the assembled turbine components in its almost completed fabrication stage. The Turbine Testing Lab at Kathmandu University consists of 2 kW Francis turbine test rig to study the operation of Francis turbine. The test rig contains framework for holding different components of the turbine. Pressure gauges are placed at the inlet of the spiral casing and inlet of the draft tube. This size can be changed according to need. Known weights are added to measure the torque. Similarly, RPM can be measured from the test rig. Manometer reading is also noted. And finally, the efficiency at different RPM is calculated using the experimental analysis, and efficiency versus RPM graph is developed to determine the best efficiency point of the fabricated Pico turbine. The computational fluid domain consists of spiral casing, vanes, runner, and draft tube. The cavity feature is used in SolidWorks to create the fluid domain from the structural domain. The numerical solution is performed using ANSYS CFX 15.0. All the components are meshed using tetrahedral elements of the mesh as shown for this figure for spiral casing fluid domain. Effects of the walls on boundary layer flow is captured using smooth flow of 8 layers of inflation with growth rate of 1.20. Now this figure shows the assembled fluid domain during CFX pre. The mass flow rate of 16 kg per second at the inlet of the spiral casing, an average static pressure of 1.01 into 10 to the power 5 Pascal, which is atmospheric pressure, at the draft tube outlet is used as boundary condition for simulation. A total of 3 interfaces are created between one between spiral casing and vanes, another for vanes and runner, and the next one for the runner and draft tube. The rest of the surfaces are set as walls for the simulation. The flow through the turbine is considered to be incompressible, viscous, and fully turbulent. The runner is considered rotational domain, while all the other components are stationary. Then, after running the CFX solver, flow streamlines, pressure contours, and velocity vectors are developed in the CFX post as shown in this figure for the runner. And the necessary parameters for the efficiency calculations are determined. Finally, similar to experimental analysis, here also efficiency versus RPM graph is developed to determine the best efficiency point for the computational analysis. Now, this is the graph determined for the result of the experimental and computational analysis. This red graph shows the data determined from experimental analysis, and the blue one shows the efficiency determined from CFD analysis, which is computational analysis. Each of these points are efficiency determined at their respective RPM points. Now this graph shows the best efficiency point of experimental analysis at 2652 RPM to be 42.8%. Similarly, the BEP for computational analysis is determined from this graph to be at 2720 RPM, which is 55.3%. So, concluding the presentation, turbine study and development is very essential in context of Nepal, and even more so for Pico hydro turbines. The research discusses the study of 2 kW casted Francis runner at Turbine Testing Lab so as to design, fabricate and analyze the components for the runner. Again, the efficiency of Pico turbine from experimental analysis is found to be 42% at 2652 rpm best efficiency point, and the efficiency from computational analysis is found to be 55.3% at 2720 rpm BEP. So the research shows efficiency from experimental analysis less than that from the computational analysis. This difference in efficiency might be a result of poor fabrication techniques and the ignorance of surface roughness during the numerical analysis. The possibility to obtain better result in experimental analysis would be to improve the fabrication techniques, such as to use hot rolling instead of cold rolling. Similarly, the welding in the surface of the spiral casing and draft tube could be improved with the use of better skilled welder. Also, the surface cleaning would decrease the surface roughness. So these methods would have increased the possibility to increase efficiency. However, these factors were excluded from the scope of the study due to the time and budget constraints. Despite these limitations, as discussed earlier, such research in undergraduate studies will benefit the students, and fabricated Pico turbine can be installed at low cost to benefit the rural areas of Nepal. Thank you very much for your time. If you have any questions, you can directly write it to me. It would be very nice to discuss with you and to contribute towards the hydropower sector in any shape or form. Also, this is the email address of our corresponding author, Assistant Professor Dr. Biraj Singh Thapa. Thank you very much.